Hi, welcome to our face-to-face meeting for STAT151. This week we are going to talk about the material in sections 2.2 and 2.3, which deals with expected value and special expectations for discrete random variables. So a couple things I want to kind of draw our attention to first. One is that when we're trying to calculate variance, instead of using the expected value formula and taking the expected value of x minus the mean squared, we can equivalently find the expected value of x squared and then subtract off the mean squared to find the variance. And that's usually easier computationally than actually sort of taking each x value, subtracting the mean, squaring it, and then doing the expected value that way. So just as a sort of quicker way to compute the expected the variance, it's usually easiest to use this formula. As a note, it also makes it so that if we know the variance and we know the mean, we can figure out the expected value of x squared by doing a little algebraic manipulation. I think one of the homework problems that might help with. So just something to note. Next thing I wanted to talk about briefly, and I think this will help with the homework problem 2.3-3, is the couple of properties of the expected value and the variance. If we take the expected value, if a and b are constants, and we take the expected value of a times x plus b, that is equal to a times the expected value of x plus b. And if we take the variance of a times x plus b, that is equal to a squared times the variance of x. So, and those properties are shown in the book, and there's some proof there. But just in terms of using them, I'm going to do a quick example. So if we have the expected value of 4x minus 5 equals 7, and I want to find the expected value of x, I know that the expected value of 4x minus 5 is equal to 4 times the expected value of x minus 5. That must be equal to 7, which means that 4 times the expected value of x is equal to 12. So the expected value of x must be equal to 3. Okay, so I can kind of use this kind of information to find the expected value of x if I'm giving the expected value of some linear combination with x. I can also find the variance of x. I know that the variance of 2x minus 5 is equal to 2 squared times the variance of x, and this must equal 20. So this means that the variance of x must be equal to 20 divided by 2 squared, which would give me a variance of 5. Now that I have this information, I could use it again to find the expected value of 12x minus 1. This is going to be 12 times the expected value of x minus 1. My expected value of x is 3, so this is 12 times 3 minus 1, which gives me 36 minus 1 is 35. Is the expected value of 12x minus 1. If I want to find the variance of 12x minus 1, it's going to be 12 squared times the variance of x, which is going to give me 144 times 5. So just kind of showing us how we can work with those properties to solve some problems. The next thing I want to talk about, there weren't a whole lot of questions on the discussion board, but there was one about homework problem 2.3-12, which worked with the geometric distribution, and I pointed that out on the discussion board, but I want to just talk a little bit about the geometric distribution. So the geometric distribution is a special distribution that can be applied to certain types of problems, and it's used very frequently in probability. If we have an experiment that has two possible outcomes that we can call one of them success and the other one failure, if we call the probability of success P and the probability of failure Q, which, since we have to have either success or failure, is going to be equal to 1 minus P, the probability of success. Then we repeat the experiment independently. So what does that mean? It means the probability of success is the same for every time that we do the experiment. We're going to repeat it independently until we have the first success occur. If we call our random variable x the number of the trial, so how many times we have to repeat the experiment until we have that first success occur, that has what we call a geometric distribution. Now, the support of a random variable that has a geometric distribution, we can see the first success could occur on the first try, or the second, or the third, and theoretically it could go on forever without it ever occurring, right? Eventually it'd be unlikely, but it could happen. So the support is going to be x is going to be an element of the non-negative integers, 1, 2, 3, and so on, up to infinity. Now we want to find the probability mass function. Remember, this is the probability that our random variable x takes on exactly the value little x. In order for success to occur on the xth trial, I need to have had x minus 1 failures happen first. So we can think of this as the probability of having x minus 1 failures, followed by 1 success. We know we have independent events, so the probability of the failures happening was q. We'd multiply q times q times q, x minus 1 times for my x minus 1 failures, and then multiply by p, the probability of success for that 1 success that occurred. So this would be having x minus 1 failures and then 1 success. Also derived in the book are the mean, which is 1 over the probability of success, and the variance, sigma squared, that's the variance of x, which is q divided by p squared. And if we want to calculate probabilities when we're working with the geometric distribution, if we think about the probability that x is greater than some particular value little x, what would this mean? It would mean that up through trial x, we haven't had any successes, right? We've had all failures. So that would be the probability of having x failures and then something else happening beyond that. So this is q to the x power. Now if we think about the complement of having x be greater than little x, that would be the probability that x is less than or equal to little x. So that would be the complement is 1 minus q to the x power. You can also think about the probability that x takes a value less than a particular value, little x. What this means, if we think about it, is this is really the probability that not all of the first x minus 1 were successes. So this means that it's the complement of having x minus 1 consecutive successes. So it's 1 minus, sorry, wait, not all, if x is listed, it means that they weren't all failures. Okay, if x is less than x, then not all of the first x minus 1 were failures. That's right. Okay, so it'd be 1 minus the probability of failure, x minus 1 power because we didn't have x minus 1 failures. And then again, we can use the complement to find the probability that x is greater than or equal to a particular value. Little x is the complement of being less than x, so that's 1 minus q to the x minus 1, which gives us q to the x minus 1. So in terms of calculating probabilities with a geometric distribution, these are very useful to kind of think through this way. So I've got an example to work on, working with geometric distribution. This is one of the exercises from the book. It's 2.3-15. In this example, it talks about apples being packaged automatically in 3-pound bags, and 4% of bags actually weigh less than 3 pounds. We're going to select bags randomly until we discover one bag weighing less than 3 pounds, and we want to figure out the probability that we would select at least 20 bags to find one weighing less than 3 pounds, the probability that we'd select at most 20 bags to find one weighing less than 3 pounds, and the probability that we select exactly 20 bags to have one weighing less than 3 pounds. So the first thing we have to think about is what we're going to define as success and failure. We're looking to go until we have one that weighs less than 3 pounds. So that is our first success, right? So even though it doesn't seem like a success to have one that's less than 3 pounds, that's what we're going to call success in this example. Success is a bag weighs less than 3 pounds. Our little p, the probability of success, is 4%, so 0.04, which means that our q, the probability of failure, is 1 minus 0.04, which gives us 0.96. So my probability mass function, if I wanted to make it, is going to say, okay, f of x is equal to q, so that's to the x minus 1, times p, so this is 0.96 to the x minus 1 times 0.04. And just to kind of go through and kind of think about it, okay, if I wanted to find the mean, mu is equal to 1 over p, which is 1 over 0.04, which is 25. And just thinking about this intuitively, it makes sense, right? If 4% of bags are underweight, it makes sense that I'd have to go about 25. I'd expect to go about 25 because, you know, that's kind of makes sense. Okay. And then the variance, sigma squared, would be equal to q over p squared. Q we know is 0.96. P is 0.04. We square that. And it's going to give us a value. I actually didn't do the calculation, but that's how we calculate it. Since it didn't ask us for it, I didn't calculate it, but I figured we just kind of put it in there. I think there's a homework problem that asks about mean and variance. Okay, so now coming back to answer the questions. Question A, I want to find the probability that we need to select at least 20 bags to find one weighing less than 3. So at least 20 means x is equal to 20 or more, greater than or equal to 20. So this means that I'm going to have 19 failures, at least. So we've got 0.96 to the 19th power, and that's our q to the x minus 1. That gives us about 0.4604 if I round to 4 decimal places. Part B asks the probability that we select at most 20 bags. Okay, at most 20 means that X is less than or equal to 20. That means I'm going to take 1 minus our Q to the 20th power. So 1 minus 0.96 to the 20th power, which is going to give us approximately 0.5580 if we round to 4 decimal places. And then the probability that we select exactly 12 bags to find one weighing less than 3 pounds. This is our F of 20, which means we're going to take our 0.96 to the 19th power, multiply by 0.04, and that gets us 0.0184. Okay. So just a little practice working with geometric distribution. Are there any other questions that anybody has that either of you have? Do you want to talk about?
No. I've had the question about 2.33.
Yeah.
So
right. Did that feel
yeah, that
also?
definitely helped.
Okay.
I was able to figure out the first 2 posts, and that I think clarified what I should do with the third post.
Okay, great. Okay. Well, if there aren't any other questions, I am just going to kind of talk just for a second about special distributions. Not really talk too much, but just kind of point out the ones we've seen already. So there are certain special discrete distributions. We just talked about the geometric. We've also seen last week the hypergeometric and the discrete uniform. Next week's module is going to focus on 3 more special distributions that can be used in certain situations with discrete random variables. And one of them is a binomial, which probably some people have seen before in STAT151. Also something called the negative binomial and the Poisson distribution. These are all presented in separate sections in this book. And so we'll cover 3 short sections in the next module. One thing I want to mention is that because they're all presented in their own section, it's very straightforward with the homework to figure out which distribution you need to use, because if you're in the binomial distribution section, you're probably going to use the binomial distribution, and if you're in the negative binomial section, oh look, it's a negative binomial distribution. No challenge in figuring that out. Usually one of the things that people have a little trouble with because of that is figuring out, if I'm given a situation, how do I know which one to use? And that's what we're going to focus on. So after next week's module, there'll be a sort of a review module before the midterm. And during that module, we'll focus a lot on being able to distinguish when it's appropriate to use each of the distributions. So I just wanted to kind of mention that. But you might want to just kind of start thinking about how the situations are similar and how they're different, and how you can try to start recognizing why this is the right time to use the distribution that I'm using. Okay? All right, if that's it, we'll wrap up for the day. Thanks.